So it's yeah, I was wondering about these lights. Dario, can these be turned on? Here?
No, I got it.
Okay.
Those are the blackboard lights.
All right, yeah, that's better. So I want to talk about invariant theory. It's sort of strange that I would give this talk, because certainly not my expertise. As I explained last week, and some of you have heard me talk about some recent work with Ankit and Raphael here, and with Leonid Gurvits, we encountered the need to use information theory actually for the analysis of an algorithm, and or the analysis of several algorithms, and it was extremely useful and powerful and also beautiful. And that's invariant theory. Yeah. I said information theory. Probably the influence of Mark's talk yesterday. Also information theory, but today it's invariant theory. Okay. So, and this is not the first time that this is happening. I mean, invariant theory sort of appeared. It's one of the, I would say, of the later fields of mathematics to join the computer science party or the complexity theory party. We seem to need to use and to interact more with various fields in algebra and analysis and information theory and number theory and so on. And there are several other places where invariant theory comes in interaction, and I want to tell you about these. And so there'll be, I want to talk about the basic problems, or some basic problems and some basic results in this very big and important field, but also to connect to them to algorithms, to optimization, to complexity. In particular, we'll see connections to lower bounds and de-randomization. And other things that we do in complexity theory. And the connections are, so some are just uses of invariant theory and results in invariant theory for these purposes. And some, I should say that from the very beginning of this field, it was born in 1845 by a paper of Cayley. The title is something like Some Problems in Linear Algebra. From its beginning and to this day, it's a very active field, and to this day, it's an extremely algorithmic field. I mean, they need to compute things, mainly invariants. So there are beautiful algorithms. Actually, in this very first paper, Cayley introduces something that's called the omega process, and I will, at the end of the talk, hopefully I'll get to show you what it is, but it's just a beautiful algorithm to compute invariants. So hopefully we'll get to see this. So I want to start. So this is going to be all very gentle and slow, and I'm not sure I probably have material for 4 hours as usual. But please stop and ask questions, and also those of you who know more than me contribute comments and expansions. So first I want to start with just my motivating example for what are invariants. Of course, invariants are something that's familiar to everybody since high school. We meet them when we talk about physics, and we talk about various processes that preserve energy, preserve momentum, preserve mass, and so on. And these, these are quantities that are not changed, so they are invariants. That's what invariants are. Things that do not change when there is a process evolving. We learn chemistry, and there are those chemical reactions, and we learn how to count the atoms on the one side of each type on the one side of the process, and the other side we see they don't change, they just recombine and stuff like that. So the invariants are present even if we didn't think about them consciously, or even if our teachers didn't call them that. So I want to show you a mathematical example that some of you know, and just to illustrate this. So here's the question. Suppose that I have this shape in the plane and this shape in the plane. Okay, two polygonal shapes. And what I'm asking you is whether I can move from here to here by the following types of operations. I can chop. I have a pair of scissors. That's all I have. So I can cut along this line. Cut it along this line. This will give me this thin triangle and also this whatever. I'm sure I'm not doing a very good job. Right? So I can cut it. And then I can cut it more, and I can also glue things. So I can maybe turn this around and glue it here. So this can go here and this can go. Maybe it will go like this. Maybe so it's probably stick out. Something like this. So I can just move this. I can cut the pieces, move them around, never overlap them. But that's all I'm allowed to do. I create any type of shapes, and the question is whether I can eventually generate this. Anybody can tell when can it be done? Area. Very good. So this possible. So if this is figure A and figure B, it's possible if and only if the area of A was the area of B. And it's not very difficult to prove. You can prove it. It's a simple exercise. So here's another question. This was in R2 in the plane. So now suppose that we move to R3. And we have the same situation. We have polygonal bodies. And let me not even draw them because it will. But you can imagine. So you can have polygonal bodies. They don't have to be convex or anything. Just like it's the same thing, only in the 3 dimensions. And I ask you whether this is possible. So when we said this theorem, it says 2 things. It says that area is an invariant. That's clear. So in this process, the total area of the pieces remain invariant. That's trivial. And this if and only if says that it's the only invariant. If you know that they are equal, then it's possible to get from one. What's the situation here? Anybody can think of an invariant? Yeah, straight lines, just straight lines, arbitrary straight lines. No, just straight lines. Now I'm allowing you, now instead of scissors, I have a saw, right? So what? Is it
clear in the first one that this is doable in a finite number?
Yeah, in fact, I insist on a finite number. If you allow infinite, you can do whatever you like. Yes, so sorry, this is finite. Yeah, I insist that you do it in a finite. That's a very good point. If you cut it to points, then yeah. So what here? So what's an obvious invariant is a volume, right? So what are the so volume is an invariant. It has to, it's maintained throughout this process. And what else? Surface if the two bodies, what?
Surface area.
Surface area is not maintained, no. No, if I mean, I certainly increase it if I take a cube and I cut it somewhere and I separate, I added the surface area increased. Anybody else?
Well, there's a stain invariant, right?
Yeah, well, okay. So here's the story. So people, this is all the places where you shouldn't answer a question if you know the answer. So anyway, so it's a non-trivial question. It's so non-trivial that Hilbert asked it as one of his famous 23 questions. It's the third question in the list of the, this turn of the century, this centennial lecture of Hilbert. It's the third question. Are there more invariants? This happens to be also the simplest question in the list because it was solved the same year, but a few months later by his student Max Dehn. So there is a second invariant, then is invariant, and that's the only invariant. It's the only other. So these are the only two invariants. You can think about this. It's non-trivial. It's sort of suggestive and in some sense related to the comment was made about surface area. It's not surface area, but it has to do with when you cut a body, the length of the edges that you cut are not exactly maintained because you are adding more, and also there's something about the angles of, the angles. So some combination of them turns out to be an invariant. A clever combination turns out to be an invariant. That's then the invariant. Okay, so.
And it was proof that these are the only two?
Yeah, these are the only two. Yeah, so this. Yeah.
Coincidence that for R2 you have 1, for R3 you have 2?
That's a very good question. I don't know. Do you know? Yeah. So the first thing I want to do is define group actions. So there is what we saw. You can study invariants of lots of processes. We are going to look only at processes which are actions of groups. I'm not going to define it formally, but these are groups, the operations that I am allowing myself, like cutting with a scissor and moving the pieces to separate or glue them. They are obviously a group in that, anything I do, I can reverse. I cut, I paste again, and so everything is possible. Obvious composition, so it's a group. So we want to talk about group actions, so we are going to have some group, and this will denote action. So this is a group, and this is a set. They can each be finite, infinite, continuous, whatever. And if I have an element here and an element here, then usually it's denoted by G of S or G times S. So you take one group element, one point, and you have this map. You have this family of maps, G from S to S. Okay, so you get, so this will be in S. And what you want is that it will be a group action, meaning that for every GH in G, and S in S, whatever. So G H of S is G H of S, and also G inverse Gs. Okay, so that's a group action. It certainly fits this model, and this is what we are trying to understand, group actions. Now, we are not going to try to understand here this in full generality. We are going to look at linear group actions. So the whole talk will be about linear group actions. So
S is a set of what? Where does S lie?
S is some set.
Any set.
Any
so
set.
like in this example,
You see, the set here is a set of these. So the set here is a set. So every element in the set is a collection of polygonal shapes in the plane.
but aren't the polygonal shapes that's the group? And the action?
No. The action is moving them to, either cutting or pasting them. So This is
Here. And this is
the group is you can think of it as moving. So okay, here is this one element of the set. This is another element. This pair of polygonal shapes.
the group is the action.
The group is what? Yeah, the separation. Yeah, or the gluing. Yes, and that's another element in the set. Okay, but here the set will be vector spaces. So we are going to. So here we'll have a linear group. So linear groups are groups of matrices basically. So G is linear, and S is some vector space. I'm not going to, I mean, you can ask me whenever you want. All the questions I'll talk about are interesting for every field. But many of the results hold only for, special fields like characteristic zero fields, algebraically closed fields. And you can always think that in the back of your mind that we are just in the complex, over the complex numbers. But yeah, of course, lots of the results generalize. Okay, so we have a linear group, and we want to understand this kind of action. Maybe we should look at some examples of this kind of actions. So the obvious example is where G is, let's say, GLN acts on F to the n. Simply, if this, if we have a matrix A here and a vector V here, then we act by A times V, the matrix vector. That's the most obvious one. We can have GLN, and GLN, it doesn't have to be, it can be some subgroup. So GLN is invertible matrices over the field. So this should be F here. Invertible matrices over the field. They act on vectors, but they act also, so for example, they act on Mn of F, which is something with n squared variables, right? This is just like F to the n times n. And the action here is A is here and M is here, and the action gives A times n matrix multiplication. So it's somewhat more complex. Another interesting action here is conjugation. We'll look at some of these and in more detail later. Conjugation. And so here we have again GLN acts on Mn, but the action is if we have A here and M here, we go to A, M, A inverse. Anybody wants to give me an invariant for any of them? Let's say for this one. Trace of what? So, sorry, trace of M is very good. Yeah, very good. So trace of M is so let's look at the invariants here. Invariants, so trace of M is an invariant. Very good. You have another? Say again?
Determinant. Oh, if it's
Determinant is not. Well, yeah, determinant. Yeah, sorry, determinant is fine. Yeah. Okay, good. So characteristic polynomial. So that's somehow that includes all of them. We know that, I mean, some of you should remember that the determinant of Ti minus M is an invariant. In some sense, it's the only invariant. We learn, that's what we learn in algebra. We don't talk about it like that usually, but that's sort of a weird invariant because it depends on something that we don't really get as input, right? So the way to write it in the language that we are talking about, invariant should be a property of the objects we act on, of the set, right? Then what you have to do is simply, there are several invariants here encoded in one, and these are just the traces of powers of M. So really the invariants here are trace of m. So what you said is 1 trace of m squared m to the n, and these are all of them. Every other invariant is generated by them in a way that we'll talk about in a second. Okay, so and I want to mention just another example. Sometimes the action of a vector space is indirect. So this, in fact, yeah, I guess both of these second, third examples are examples that are more indirect than that. And I want to give just one more. If you have, so GLN can act on some polynomials, so polynomials of degree d in x1 up to xn. And the way this action happens is that A acts on some polynomial p of x, to yield, so AP is p of AX. So you apply the linear transformation to the variables and then expand. So this is a linear action on what? It's a linear action. What is it acting on? What is the set here? Not f to the n. No, not f to the n. Yeah, it's the set. It's a vector. You know, it's so S here is I guess all the n plus d minus 1 to the coefficients of p. Right? It just transforms the coefficients so in a linear way. And we'll talk about this. This will be important example. Okay, so we've seen there this example and the invariants for this conjugation, and actually this is a good example of exactly what we are going to study. When you study linear actions, the invariants will always be polynomials. So invariants of linear actions are always polynomials. So they're always polynomials. They are not always polynomials. If the trace of m is an invariant, also the sign of the trace of m is an invariant, and the log of the trace of m is an invariant, and so on. They are not polynomials, but all other invariants just factor through the polynomials. So we are going to define a polynomial, the invariant ring of polynomials, and so the invariant ring, it's denoted by, so if we have g x on f to the n for some n, so once it acts on f to the n, acts on x1. So we have this action on the vector space, which we can think of, I mean, just on this vector space. It acts on all polynomials in these variables. And then, so maybe I should say it like this. If it acts on f to the n, then g also acts on, right? It acts on vectors, so the vectors can be plugged into the variables of polynomial, and we denote the usual notation is, so x will be my set of variables always, and sometimes we will not know exactly what they are. Okay, so f of x with exponent g is just a set of all polynomials p which are invariant. So for every g in g, gp. Okay, the gp is exactly meant just like here. Okay.
Is it the same in and purpose? So you think if you have
It's not the same, it's some arbitrary n. This action doesn't have to be by, now it's an arbitrary group, so it can be a much smaller.
Yeah, but you say you have an invariant, G acts on F to the n implies G acts on F to the?
Yeah, so what does it mean G acts on F to the n? It takes a vector of length n and produces another vector of length n.
Exactly.
See, just feed this vector to the polynomial.
Okay, that's
That's what I mean. Yeah. And now, so you have polynomials. There is an action of the polynomials, and the invariant polynomials are exactly those that don't change when under the action. And so we have, so in this example, if we have, we can think here of M. You can think here of M as just a matrix of variables, x1, 1. So in this n, so these are n polynomials in this n squared variables. They are the invariant ring of of conjugation. Okay, so we have the definition of the invariant ring. You should see that it's a ring, right? So it's an algebra. It's closed under addition. I mean, if two invariant polynomials, I add them, I multiply them, they remain invariant. So that's good. So what do we want to understand? We want to understand this for particular groups and sets they act on, vector spaces they act on, and the goal, the dream of invariant theorists is to do this. If you have this, then you achieved your goal. What are these? This you know? You don't. This is the first fundamental theorem, and this is the second fundamental theorem. That's how they call them. So, and let me tell you what they are about. So, a major result of Hilbert. So, I said that the field started with Cayley, but perhaps the most important paper in this subject and in lots of other subjects in commutative algebra was the paper of Hilbert in 1890. And in which he proved, so he was studying linear actions of polynomials. It was not the only, following some work before him. Linear actions, and was focused on, I'm not going to define it, but some people know. So G is reductive. Basically means that its representations can be partitioned to irreducibles. Any representation of the group is a direct sum of irreducible representations. But anyway, there is some notion. This notion includes everything we'll talk about, which will be mainly things like GLN and SLN and SN. So groups we like, you don't have to think about this, but he proved it for all these groups, all the reductive groups. What he proved is something amazingly, it's striking and important. The polynomials come in all degrees. Invariant polynomials also come in all degrees. So this is an infinite ring, but what he proved is that this infinite ring is always finitely generated. So for G reductive, G is finitely generated. And I'll denote it like this as P1, Pt for some finite t which generates. And generates, I mean, as an algebra, right? You can take these polynomials and add them and multiply them, and you get all invariant polynomials. To prove this, I can give, maybe I'll delay to the end some proofs that are short. This has a very short proof once you do all the all the background work that he did in the same paper that many of you know and some of you use, the Null-Salenzas theorem, the finite basis theorem. This was, this was all a sort of a prelude, something he had to do to prove this. That's what he wanted to prove. Or maybe, anyway, that was definitely a goal for Hilbert. Once you know this, the proof here is relatively simple. I should say that, okay, I'll say something about it. I will not give the proof, but I'll say something about it. And then we'll start, so once you have finite generation, you want to, okay, what are these finite number of polynomials? Now we know that there is a finite description. Let's find them. And in fact, let's see that they are also useful to have for various problems. In fact, like here, right? This is basically questions about isomorphism testing of objects. So I want to say one thing about the proof and about the way to get invariants, and we'll see some more later. Is what would be a natural way to get invariant polynomials? I mean, I give you some polynomial. Clearly, you can make it invariant. What would you do? So suppose the group was, suppose that G was finite, and these are there are some good examples of this. Or maybe before I do this, let me do just some examples. Okay, I just want to give you a couple of examples where we fully understand the first and second fundamental theorem. So let me first say what they are. First fundamental theorem is to get a finite set of invariants that generate the whole ring. The smallest the better, or the nicest the better. We'll see non-trivial examples, and we'll even require more of this set of polynomials. And the second fundamental theorem is about understanding the relations, the algebraic relations between the invariants. So, I mean, this sounds abstract. I want to give you two examples that you are all familiar with. So, in which you have these FFT and SFT, and they are the canonical things you would really like to, the understanding you would like to achieve in all cases. So, let's say Sn acts on n, and also so on. Right, so symmetric group on n elements just permutes the elements 1 through n, and so it permutes the variables. What are the invariant polynomials here? Yeah. So they are all symmetric polynomials. That's why they are called symmetric. And here it's not very difficult to see that they are, these are all. And they are generated, we know what they are generated by, right? I mean, they are generated by the elementary symmetric polynomials of degree up to n. We don't need more if we act on n elements. And this is actually the same as just it's simpler to write sum of xi squared, sum of xi to the n. So these are generators for the symmetric polynomials. Notice that we understand that's like a first fundamental theorem, and the second is just observing that there are, not observe, you need to prove that there are no algebraic relations between them, so they are actually algebraically independent. So we understand everything here. You can also notice, if you want, that this is the same as this, only that these polynomials are polynomials with the eigenvalues of the matrices. So, anyway.
You're probably not worried about this, but the characteristics.
Yeah, so I'm not worried about that in the sense that whenever you have a counterexample, think that we are moving to C. Yeah, that's right. There are lots of statements that I make that are not true in general. They are true in, under some conditions. Here's a second example. So we already have this example, of course, which is also a complete understanding. And the second example is SLN acts on Mn simply by matrix multiplication. So so A here acts on M here, simply A times M. So these are the invertible matrices of determinant 1. Okay, so what is what doesn't change in this action? What is symmetric? Yeah. So here, right. So X is now these n squared variables, and it is generated a determinant. It's the only invariant. The determinant is the only invariant here. So also here we completely understand the FFT, SFT. Okay, so I want to let me just see if no, okay. I want to as a ring.
But can't you take any, take determinant times any other polynomials?
No, determinant times x11 is not invariant. Definitely not as a ring, as an idea. It's just as a, yeah. So in this case, just powers of the determinant. That's the only thing. Okay, so I want to start doing some more complicated examples, and also which are also motivated. Until now, there's no particular motivation from anything we do. You can still ask yourself, how are these done? I mean, we learned them in algebra in high school, but nobody told us how to do it. Maybe I'll tell you one more example, and maybe we'll prove it at the end. This is, in fact, the problem that started Cayley on this, and Gordon, and so on, is the action of SL2 on basically F cube in the following way. Is on polynomial. So you really you interpret this as a polynomial, binary form of degree 2. So here, a 2 by 2 matrix acts on ax squared plus bxy plus cy squared. So this is a binary form. It acts by just acting on the variable. So this polynomial p of x is going to move to the polynomial p of ax. Okay? So it's just the type we discussed somewhere over there. What are the invariants of this? You know, what property of when does whenever we act on, we get ABC.
Sorry, what about the notation? You're thinking of y as a variable? Is it?
Yeah, it's not good notation here. I should have called my variables differently. Here, my variables, so the variables are, A, B, and C.
So the polynomial takes a, b, and c
to some other, to A prime, B prime, C prime, after this change of linear change of variables x and y, right? What did we learn in high school or in college about the invariance of this? Anybody remembers? Yeah. So the invariant here is what's called the discriminant. Again, they didn't tell us where it comes from. The discriminant of this binary form, which is b squared minus 4ac. Turns out that this polynomial, after any change by any matrix A of determinant 1, remains the same. So that's the only invariant. Okay, so these are simple examples. Now I want to go to more complicated examples. But before that, I want to talk about orbit problems. First of all, questions. Nobody, or maybe I had some questions, but anyway, everything is okay. Okay, so let's do some more examples and of orbit problems. So all of the examples I gave are, immediately give rise to orbit problems. I give you two matrices here, and I ask, are they conjugate? And you know what to do. You evaluate these n functions, and if you get the same answers for both, then they are conjugate. If you don't, so that's the value of having a small, concise set of invariants. What? Yeah, actually, I didn't talk about closure yet. Yeah, it's almost. But actually, I should, maybe symmetric. You want to know whether whether two vectors of numbers, x1 through xn and y1 through yn, can be permuted to each other. Well, you can check it just by looking at it, but another way to do it is just by evaluating these functions and seeing that they are the same for both. So these are simple examples. I want to talk about more complicated examples, and there will be two important ones, but that we will continue with, but I want to talk about a few more. Okay, so one is simultaneous conjugation. So what's simultaneous conjugation? Here the action of, let's say, SLN, in this case can be GLN, acts on not on one matrix, but on many matrices, Mn to the M. And the way it acts is, A acts on M1, Mn, sending it to A, M1, A inverse, A, M1, M. Okay, so this is already a complicated action. It took years took a century to find the invariance of this action. I just want to, Ankit just made a comment that corrected me when I was talking about just normal conjugation. I'm going to tell you the connection between orbit problems, like telling whether two objects can be moved from one to another by a group element, and the values of the polynomials in the invariant ring. And this connection is not so simple as you might think. It's all in the linear algebraic setting. In the example here, area captured exactly whether two things can move to each other, and here these two things captured exactly. So we can ask, even in conjugation or in simultaneous conjugation, when are two tuples in the same orbit? So we can ask, I give you, so here's an orbit problem, so this is a collection of orbit problems. So given M1 to MM, and maybe N1, two tuples of matrices, does there exist a G, in this case GLN, in G such that G is a vector M? So this is a computational problem, and actually it's a very important computational problem. Some people recognize it, I assume, as this is a module isomorphism problem. And we would like to say, would be nice to say that we can test this by simply evaluating if we knew, even for m equals 1, even for m equals 1, simply by checking that all these polynomials, invariant polynomials, have the same value on the m and on the n. That's what you would wish for. It turns out that it's not going to work. Why is it not going to work? In this linear algebraic setting, and here all I'm thinking about, you should think about C or about, other fields that have metric topology on them, but you can just think about C. If here's an issue. Suppose that all polynomials in a set have some value on a sequence of tuples, and this sequence converges to another tuple. Then, because polynomials are continuous, the values will remain the same. So if we denote by, so okay, that's a modular isomorphism problem. If we denote by OG of, in this case, let's say M, the orbit if we denote it, and we happen to have M, how do I denote? Let's put it 1 here, M2. An infinite sequence of tuples, you can think of one matrix as the same thing, but anyway, of tuples, which converges to some other tuple. If all of these guys have the same value on a given polynomial, then the limiting object will also have the same value. Okay, so what this suggests is that looking at orbits is good, but looking at the closure of orbits is...
Okay, what's the definition of orbit again? I missed it.
Orbit is just, maybe I should, so that's a very good question, and I should just write it. Should have written it there, but if we have G acts on S, this is completely general, then the orbit of G of some element S is simply the collection of all other objects that you can get to. So it's simply GS, G and G. Okay? So if we have some V is P of M1, P of M2, and so on, this will imply that V will also equal P of M for some polynomial. So what this suggests is that we should look at orbit closures, and then having the same value of invariant polynomials will tell us the value. It will tell us whether two things are in the same orbit closure. So I'll be more specific. Just a second. Okay, so we want to look at these objects. Well, maybe something here, some element, yeah. And we want to close it. So this is a set. OG of M is a set. It's, for example, a set of vectors of matrices. This is their closure where we, yeah, so I should specify what we mean. Yes?
So when you said invariants are just polynomials there, that's not really true, right?
Yes, that's right. So, no, it is true that the polynomials are the only invariants.
Because like the number of the orbit in which they lie is also invariant, but you're saying it's not completely polynomial.
Okay. That's yeah. So yeah, that's a very good point. Yeah. So in this setting, the polynomials are not all invariants unless you close the orbits. Yeah. So that's yeah. So so I don't want to be too formal here. I just want to note that in this picture that I just drew, when I said converge to, there was an obvious meaning in your mind. If this is over the complex or there is, then we understand what convergence is, and there is like a Euclidean convergence. So this is we are closing. So we have a set in the in C to the n or R to the n or something like this. So closing it, we can have two meanings. One is doing it in the Euclidean or in the metric that's natural for the space we are over sense. And another sense, which is if you're an algebraic geometer, the way you would close a set, you would just see what polynomials it vanishes on, and then add all the points that vanish on all these polynomials. So close it as an algebraic variety, and this is called Zariski's closure. And it's really important that even though these are completely different definitions, and in many cases they are not the same, in this story, when we are studying actions of reductive groups on vector spaces over, I think, algebraically closed fields, but even more than that, then we have these two senses together, and therefore we can just restrict ourselves to understanding orbit closures in whatever sense that is convenient at the time. And now we can go back and ask the question about this. So given two tuples, are they in the same orbit closure? So the question that we really care about is given two tuples of matrices in this case, M and N. We want to know whether the orbit closure, so one basic question, or one orbit question that's very basic, is whether these two intersect or not. Okay, and they intersect, and this will be if and only if they intersect, so this will be not if P of M equals P of N for all invariant polynomials. Okay, so that's a fundamental theorem. I should say probably this is once we started taking closures, we are moving to geometric invariant theory, and the main person responsible for developing it after Hilbert is Mumford. So that's one question that we will ask ourselves, and it turns out that for this problem, for this particular simultaneous conjugation problem, we will see that it can be done in, so this problem can be solved in polynomial time. This, I'll talk about this in a second. This is results of Malmali and Forbes Spilka. And that's a really nice connection, because the best way that invariant theorists could solve this problem was exponential time, using various Grobner basis techniques. So I will tell you soon what led to this and how it's related to de-randomization. Okay, that will be one type of result. I just want to mention that the result here, that the question I asked originally, this module isomorphism problem, which has no closure in it, there's no closure there. It's an interesting problem. It's maybe even more, to some people, more interesting than the problem with the closure. This has also a polynomial time algorithm, in fact, for every field, using completely different techniques. So this is also in P. So this was known, and this is sort of irrelevant. I just want to say that this kind of problems are also looked at and are solvable. This is Brooks, Banks, and Lux. Yeah.
I would guess from the answer, when you only have one matrix,
Very good.
The largest degree.
Very good. Yeah. So we'll, not n.
Let alone
Yeah, that's let me.
Anytime you use polynomially many invariants, or the algorithm that finds them enters it in some scheme which.
So let's get to this in a second. But your guess is right, although it took a long time to check that these are all. So I'll say it more explicitly. Just a second. I want to talk about a couple more orbit problems and their relation to CS. So here is another, in fact, a special case of this problem, of the first problem. Sometimes, yeah.
You mean there are closures of the orbits then?
Yeah.
Yes. Thank you. Yeah. If I forget, remind me. Thank you. The orbit closures. Yeah. And the second is a special case where you just want to compare one. So I'm writing here M and N as vectors of matrices, but you can understand this as just, for any action. These are objects that are acted on. Okay. But it's in P for this particular simultaneous conjugation problem. Another problem we can ask ourselves, so maybe I should write on the side the problem thing, so we have Gx on some, maybe C to the n. So one question was whether OG of something, closure intersect OG of n. That's one basic question. It's in P for that particular group action that we discussed. P of n for all invariant polynomials. And the second question is a special case of this question where, let's say, n is a 0 point. Okay? The 0 vector, right? We are acting on vectors, vector spaces. The 0 vector doesn't remain 0. So the orbit closure of 0 is just a point 0. All polynomials, I should say, all polynomials, all invariant polynomials, you can assume that this ring has just homogeneous polynomials. And we are going to consider them only those. Of course, a constant is a homogeneous polynomial that's invariant under anything. So they are not interesting. So we care about just degrees, polynomials of positive degree. Okay. So suppose n is 0. So one thing we can ask ourselves is whether 0 is in the closure of a particular orbit. So we want to know whether OG of M contains 0. And this, by what we said, this will be if and only if P of M is 0 for all invariant polynomials. That's okay. That's a special case. But this particular question is called the null cone problem. Null cone problem. So this is the question is whether M is in the null cone of the action. I'm not going to motivate this. Well, I'll give you in a second example where it's where you want to compute it. But it has to do with in geometric invariant theory, you have a group action on a space. You want to sort of mod out by the orbit and look at the space you get, right? Once every orbit collapses to a point, what topology, geometry, and so on it has. And in particular, you have to understand which points go to 0, because these are the points you want to remove. So anyway, it's a basic problem there, but in particular for us, and I want to mention it here, is so I want to mention another group action first. So here we talked about simultaneous conjugation. Conjugation, that's an action by one element from the group SLN or GLN. Now I want to talk about actions. Maybe I should move this also there so it will be visible what an orbit is. Okay, so I want to define one more action here, and this action is called the left-right action. We'll soon take a break. I'll just finish with the examples. The left-right action. So here you have SLN cross SLN act on a tuple of matrices, or on Mn to the m, and the way A and B act on a tuple M1 M is by sending it to AM1B, AMM. Okay? So it's a different action. It's not, you don't conjugate. You have a change of basis from the left and from the right that are independent from each other. And this, so I'll tell you about this in detail also after I tell you about this one. But I want to say that in this case, so for simultaneous conjugation, we said the problem is in P. The orbit intersection problem is in P. And for the left-right action, and this a result of, as I mentioned before, Garg, Gurvits and Olivera and myself, and then later by Invariant Theory. This is really over this for C, and that's for really any field. Invariant Theory and Subramaniam. So the result is that here the null cone problem as a polynomial time algorithm. So the null cone, again, I give you a tuple of matrices. Can you change basis so that you approach 0? It looks like it's not interesting at all, and why should anyway? These guys are mostly in the algebraic place, but this is extremely important. And again, those that heard me talk about, anybody else talk about operator scaling, this solves several really, I would say, diverse problems in mathematics. They solve the word problem. So knowing this, you are able to solve the word problem for non-commutative fields. You are able to determine the rank of non-commutative rank of symbolic matrices. You can determine the constants in Brascamp Lieb inequalities. That's what I talked about last week. And so it somehow is extremely useful. And one way to look at this question here about this null cone question, which is another general question that one might ask. So it's another question that one might ask, given that we understand that convergence can be taken in both this Euclidean and this Zariski sense. A general problem that you can ask is an optimization problem, and that's also a view that we took there. What is a natural optimization problem in this setting? A natural optimization problem, when you have some, maybe I should, okay, again, you should think of it as C or R, is to ask the following. This is an optimization problem. Let's say in the 2 norm, you can take any norm you like. So what distinguishes points in the null cone from points not in the null cones are that, you know, the first can be driven to 0, so the solution to this infimum, to this optimization problem is 0. If it's in the null cone, you get 0 here, and if you are not in the null cone, you get some positive number. It turns out that this positive number, bounds on this positive number, are essential to the analysis of this algorithm. So getting good bounds, and maybe I'll show you in the second half, getting good bounds here on the algorithm, getting polynomial bounds. So understanding
unit vectors or something?
What?
This is over all V?
All V. All V. Well, this problem is really you're given V. You are given V and you are asking, so that's the info. I give you V. You want to know whether it's in the null cone or not. So I give you V and you want to know. Okay, and the last problem I want to.
Sorry, can I ask a question?
Yeah.
When you say it's over C, what does that mean computationally? So you're saying you have.
Yeah, the inputs are rational. You can the inputs are rational numbers, and in terms of their bit complexity, it will be input.
Okay.
Yeah, yeah, that's a good point. You cannot. Okay, and the last thing I want to mention is a problem that I think all of you know about, and this. For a general group action, you can ask a question, which is somewhere in between, well, somewhat weaker than this. You can ask a question whether n belongs to the orbit closure of M. Okay? So it's not quite whether the orbit closures intersect, but whether one particular element you care about, but it's not 0. 0 we already saw. So some general element is in the orbit closure of another. And it turns out that a particular special case of this is whether the permanent polynomial on n by n matrices is in the orbit closure of the determinant of m by m matrices under a linear change of variables over these m squared variables. This question is equivalent to, so for m, which is polynomial in n, this question is equivalent to the P versus NP question in the algebraic setting. So this very important, very natural problem can be asked as a question about, as an orbit problem, right? And this connection and this field is started off with Malmali and Sohoni in a series of works that they call this direction or this approach to proving lower bounds the geometric complexity theory, GCT. So I'm not going to talk about this, but this is a special case of something we saw in one of the examples of the action of a group on the coefficients of a polynomial, right? So the determinant is a polynomial, change of basis in the variables of this polynomial, and the m squared variable of the polynomial give us another variable of the polynomial. And the question is whether the determinant, whether the permanent is one of these polynomials. Of course, this is a degree m and this degree n, so you have to just add some variable so that this will be a degree n polynomial, but that's a minor point. Okay, so questions so far? You want 5-minute break? Avishai, you're the... What?
I will not...
You will not be the only one. But I can continue, or anybody wants a break, we'll take a break. Yeah, okay, good. Yeah, take a break. Okay. Very good. We'll just go in order and I'll tell you what I have time to tell you. So So I want to tell you now the invariants of these complicated actions, the left-right action and the simultaneous conjugation. And then we'll see why, in particular, having FFT and SFT may not be enough. I have here the definition of simultaneous conjugation. So I want to talk about the simultaneous conjugation and the invariant ring for this. So we already saw that when we do the action of GLN on Mn by just one copy by conjugation, so AM goes to AM A inverse, the invariant ring so these are here we have n squared variables, right? It's just generated by the traces. And that's a nice guess and very natural guess to think that if we are now acting on m copies of this. So we have again a m1, a inverse, am. That you will get something similar. You will get traces of products, and indeed this is true. So, but now it's highly non-trivial. It's an important theorem. Even here, proving that. I mean, I don't think it's that hard to prove that these are all of them. It turns out that so here's a theorem, and this is by Brascamp and then Razmislov. This is mid-70s. And really, Brascamp is the one who started generating the techniques to write down finite number of invariants for actions of this type. He studied something more general, which is called quiver invariants. It's a special case. And so the G in this case is the following. So you want to say, let me take traces of products of these matrices. I have now M. Right now I'm asking you, I have x1, x2, xm. These are matrices of variables, so these are m times n squared variables sitting in all these matrices. And it's not difficult to see that a trace of any product, if I take the trace of x1, x2, that it's invariant, right? Because conjugation cancels in the middle. So you want to say, so I take here a product of xi1 up to xi maybe t. So this type of product, and I1 up to it are somewhere, one of these M matrices. And the question is, how many t's to take? I mean, what length products you should take? And it's not trivial. The original bound of Brascamp was exponential in n being, n or m times n was exponential. And Razmislov proved that t does not need to be taken more than, I think, just n squared. But we know, it's comment that t is greater than n squared over 8. So you cannot take a linear number. So we know really the optimal bound essentially on the generating set. So that's a very good understanding of the invariant ring. And there it's true. Then if you wanted to compute orbit closure, what would be your problem? Orbit closure intersection. That you have to check the value of all these polynomials on your, matrix tuple. That's not so easy because, well, each one of them is easy to compute. That's one desired property, that you have polynomials that are easy to compute. But another that you'll have few of them, right? And there are exponentially many of them. So what can be done? I don't think that anybody thought about it much, except for realizing that it's difficult, until Malmali wrote a really nice paper on what's called Noether normalization. It's a basic thing that Hilbert used. Hilbert proved also. I don't know why he called it Noether. I mean, of course, they worked together, Emmy Noether and David Hilbert. And Emmy Noether is also one of the pioneers of invariant theory. He made the following, so Hilbert made the following observation, which is called Noether normalization. You have here an exponential, in fact, it doesn't matter how many polynomials you have here, a finite number, but in some small number of variables, and they are invariant polynomials, you can shrink this number of invariant polynomials to basically the number of variables. How would you do that? That's a very easy question to computer scientists. You have this bunch of polynomials. It doesn't have to be these polynomials. You have, I don't know, P1, P2, Pt in n variables. If you want, we generate, you want to know their values at a particular point, and you want to distinguish any 2 points which are separated by at least one of them. How can you replace this with a much smaller number of polynomials?
Take a random combination?
Yeah, take a random linear combination. So you can take sum of alpha 1 p1, so some alpha I pi. That will be one good combination, but it's not enough because we have n degrees of freedom here. So we should take j, and we can let j be between 1 and n plus 1. If we take n plus 1 random generic linear combinations in the original polynomials, then this will also separate anything that was separated here. This is a standard kind of, that's great, and that's Noether's normalization lemma. The problem is, what are these alpha i's? And notice that in this sort of randomized algorithm, you need to take exponentially many random numbers. So what do you do? So this was left open until Malmali addressed it. I mean, so this takes exponential time even if you do it this way. He asked what is an efficient way to do it, let's say for these guys. And he came up with a really beautiful answer. He said, you don't have to do it this way. You can do something else. You can express all of these traces sort of simultaneously in one polynomial that sort of should remind you of the way the characteristic polynomial captured all of these, right? It was one polynomial with an extra variable. So I said, let's add a variable, and let's look at the trace of the sum of, let's put some parameters, maybe lambda I variables, lambda I xi. And let's take this to the power k and do it for k between 1 and whatever it was, the degree here, n squared. Look at all these polynomials. When you expand them, you find as monomials all of these guys, right? With some coefficient that depends on the product of the lambda i's will tell you exactly which you selected. So why don't we just compute this thing if we want to distinguish two tuples? And in fact, it works. really nice probabilistic algorithm for the same problem, and now the number of, I mean, okay, these are variables, but these are new variables, but you can then substitute random values for them, right? For any concrete inputs, if the high probability, you'll get a separation if there was one. So that's already, this result already puts it in random polynomial time, the problem of, so this orbit in orbit closure, disjointness. Random polynomial time algorithm. So that's kind of a new addition to computational invariant theory, this idea of having a probabilistic algorithm. But normally also asked, you know, is there a deterministic algorithm? And even for some reason that was never clear to me, conjecture that there isn't, and there cannot be one. Even though in computer science we already have a religion that everything that can be done probabilistically can be done deterministically. We in fact know it. We just are missing some small part, like of the type P is different than NP. But you know, based on things we believe strongly, that everything that can be done in randomized polynomial time can be done in deterministic polynomial time. So, and this was done by so a result that is in P was by, as I mentioned before, by Forbes and Spielka. And it's really beautiful because it connects to something that I didn't completely discuss, but related to what I said about null. So
when was this result? The fact that it's in P, the Forbes Spielka?
What is the question?
When was it?
2 years ago.
Okay.
So this is like 3 years ago, and this is 2 years ago, immediately after. It turns out that this is a de-randomization problem of a type we know. This called polynomial identity testing is a general question of having a symbolic determinant or a polynomial, and you want to test whether it's identically zero. I'm not going to define it formally, but I talked about it here several times. But it's a special case of this type of problem. We don't know how to solve it in general. We don't know how to convert probabilistic polynomial time to deterministic polynomial time without assumptions. But in some cases, which are expanded every year because we understand better and better when you can do it, in particular, these guys had a way to deal with polynomials that are of this form. Okay? So there are really two results here. One, well, let me leave it as a polynomial time algorithm. Now, the reason I said it's sort of the connections are really nice is that this polynomial identity testing problem, just testing whether, let's say this polynomial is identically zero, right? In polynomial, these are given now, and this is, I am asking whether for all lambda i's, I get a zero. This is like asking whether this input is in the null con. Okay, so this particular null con question can be answered in P, and that's a special case of the polynomial identity testing question, which is the same as the question. I don't remember when I talked about it here. I'll just write, maybe I'll write it here.
The de-randomization, is the way that it works, it gives you a collection of lambda i's that you plug in?
Yeah. So that's a very good question, and I hesitated whether to elaborate here or not. The elaboration is like that. There are two algorithms in this paper. One in which I give you the actual polynomial, like this one, and then it just massages it in various ways and tells you whether it's identically zero or not. In some sense, it will find a coefficient which is non-zero if it's non-zero, but will not give you lambda i's. That's a polynomial time algorithm. And the other result, which is slightly super polynomial time, so like n to the log n, will give you just a set of, a collection of vectors to plug in for the lambda i's. And if it's non-zero, one of them will work. That's called the hitting set. it will hit a non-zero of the polynomial. Yeah. So this PIT problem, maybe I'll just, as I said it, even though. So imagine that you have an n by n matrix in which in every L, so that in every coordinate sits a linear form, Lij, of some, maybe n variables. Okay, it's just a matrix of linear forms, and let's say it's n by n, and it's in n variables. And the PIT question is given L. How is L given? It's just the coefficients of these linear forms in all. You can think of this matrix L as simply some AI xi, where AIs are in your, matrices in your field, whatever underlying field you have. So given L, you may want to compute, let's say, whether you may want to compute whether the determinant of L of x is not identically 0, or is it identically 0? And maybe more generally, you can ask, compute the rank over the field of rational functions. So these are the basic questions that we know how to solve in probabilistic polynomial time, but not in deterministic polynomial time, except for special cases like this, where we can do it in deterministic polynomial time. And that's a huge question. And here, so maybe I'll add another detour. Solving this question, whether this has a, so that's a, so PIT, it is in RP. It has a random polynomial time. You just plug random numbers to the variables. But if PIT has a polynomial time algorithm, deterministic polynomial time algorithm, then this, let me just put so if you find a deterministic polynomial time algorithm for this problem, you proved P different than NP in the algebraic setting. I put it in parentheses because it's not quite that, but it's almost that. So I'm not going to explain the parentheses, but practically that it will prove a lower bound that we are far from knowing what to do about. But one thing to, of course, note is the amazing thing that an algorithm gives you a hardness result. Another thing to notice is that this is a different attack, completely different attack on separating VP and VNP that I discussed before, which is the Malmali-Sohony attack via geometric complexity theory. But the third connection, which I find is really nice, is that we, in the paper I mentioned before, we wanted to solve this problem. We couldn't solve this problem. And our ability to, I'm not sure where it is, but our ability to compute in deterministic polynomial time membership in the null cone of the left-right action implies that if we just replace the PIT problem, replace this, compute the rank of L of x, which is a normal rank when the variables commute, if we just replace this problem with compute the non-commutative rank, so non-commutative rank of L. So I'm not going to define it, but it's an analog of rank when the variables do not commute. This problem is in P because of the algorithm that I mentioned before. So somehow, things connect in mysterious ways. They all connect back to invariant theory, which is one of the reasons I'm talking about. So, okay, so I want to take this detour, but the randomization of special cases of PIT leads to efficient algorithms in invariant theory, like in this case. So now I wanted to mention the left-right action, which gives this. So let me. Questions about this? So I should already, I meant to ask it at the end, but I'll ask this, I think, really interesting open question. So this algorithm follows from the fact that we can compute membership in the null con of the left-right action, which I define and will define again. So this follows because whether L is in the null con, L is just a bunch of matrices, right? L is just a bunch of matrices, so it's a tuple of matrices. A1 null con of the left-right action if and only, so this is L, if and only if rank, the non-commutative rank of L is smaller than N. It's sort of singular in the non-commutative setting. And that's why we can do it. We simply have an algorithm that tests membership in the null con. This raises a really, compelling question. Maybe also PIT. So maybe the commutatively singular matrices are the null con of some other action. And if we could represent it that way, maybe an algorithm like ours or different than ours would solve it in deterministic polynomial time. So the question I want to ask is does there exist a group, and well, it will act on the, so acting on A1 AM, so that this tuple A1 AM is in the null con of this action, if and only if, so this is L again, if and only if the determinant of L as a symbolic matrix is 0. It's just a PIT, just encoding the PIT question as a null con question. We have algorithms to solve some null con problems. I'm not sure it will solve this one if you discover it. And it's also possible that PIT problem is not a null con problem. We don't know. Anyway, so that's I find a really nice open question. I want to tell you about the questions about this.
That's the same as saying that the ring of invariance is just the determinant.
Yeah. Yeah. But this is a symbolic determinant. Yeah. And let me tell you what are I'm going to tell you exactly what is the invariant ring for the left-right action. So the one capturing this. You'll see it's more complicated. It's not just a determinant. Also here it may not be the determinant, right? You need a yeah. Okay. So let me say what. Okay. Good. So left-right action. So again, here we have SLN squared acts on. Right, and the action here is that M1 up to M moves to, so here we have A and B, moves to A, M1B, A. And what is if so the variables we have are M matrices as before, as in the simultaneous conjugation. We want polynomial in this M times N squared variables that do not change under this action. Okay, so you can look at it, you can see immediately that the determinant of M1 is something like this. In fact, the determinant of any linear combination of them is invariant. But that's not all. In fact, here's an infinite list of invariants. This is an important theorem that was discovered simultaneously by 3 groups, Dirksen, Weyman, Domokos and Zubkov, and Schofield and Vandenberg, around the year 2000, and they found that the invariant ring is generated by the following polynomials. I'm going to write an infinite number.
You've been here a long time.
Yes. So not just linear combination of these matrices with constant coefficients, but also of these matrices with matrix coefficients. So we want to write some xi tensor product di, and this should be, so this set is, we look at every d and every di which are in MD. So again, you take linear combinations of your matrices with matrix coefficients, so you take the tensor product. So this matrix will be ND by ND. You compute its determinant. So you have all these infinite number of matrices. That was the first result. And the next obvious question was, okay, we know we have finite generation, right? So when we talked about simultaneous conjugation, I told you they, Prochesky and Brascamp proved an n-squared upper bound on the number or the degree that you need to take. And the question is, what is the, where can you cut it off? Maybe, there should be some finite d that will cut it off. So maybe let's call d star the smallest d needed here. And we know by Hilbert that d star is finite. And there were some explicit results. So this is 1890, this is 1980 roughly. This something like a W exponential in n. And then Dirksen, around I think 04, proved that d star is less than exponential in n squared. And this result, this was critical to the work that I mentioned, to our to the GGOW polynomial time algorithm for the null cone of this section. This was used heavily in this result, the null cone of this action can be computed in P. So structural results in invariant theory lead to algorithms which can be viewed as, for example, I mentioned the optimization problem. You can solve this optimization problem, which is interesting in particular. In fact, we can compute this even when it's not zero. We can actually compute this number. So that was that. But then, just like 2 months after we did this, Dirksen and Markham. So this is a question whether this is the best bound possible. And Dirksen and Markham prove that d star, it's actually a different d star. But let me not prove that this is at most. So we are talking about smallest d, smallest. That's an n minus 1. And I want to show you this proof. Okay, so it's a question in general: how do you prove upper bounds on degrees of generators in invariant rings? I want to show you one example of how you do that.
But for you, the exponential bound was enough.
Yes, sort of amazing that the exponential, because this algorithm has an exponential convergence, something like that. So it was enough.
And given the new thing, does it make it like significantly easier or something?
No, it makes it. It makes something even better. This implies the IQS result, which I mentioned before. This was over C, or over R, over the rationals, and this was the same over any field. So there's a very different algorithm, more combinatorial. This is sort of an analytic algorithm. There's a more it's a very important result for this purpose. It does, I mean, they are incomparable in some senses because some things they compute that we don't know how to compute, and something we compute like this optimization that doesn't even make sense in finite fields and so on. But anyway, it's a very important thing, and I wanted to just show you how the degree upper bound looks like. Because this particular one happens, I should note that up to here, these results are very general. They hold for all actions of reductive groups. This is particular to the left-right action. So it's not like this improves all of this, but for this action. So that's what I want to show you now. So what I mentioned that I'm changing the D star on you. All I want is the following. These are the invariants of this action. You can ask what is the smallest number, smallest D, so that when you cut it there, you generate all of the other invariants. That's the basic, the one natural definition of D star. And the other, if you are only interested in a null cone, you can ask what's the smallest D, so that if it's 0, if the evaluation of all these is 0 up to that point, it will continue to be 0 forever, and then you know you are in the null cone. So I'll take the second interpretation. Okay. So let me tell you how to do it. For this, I need a definition and some theorems that or some results that I will not prove. But the basic thing, so let me use this notation. So I'll think of L is, you know, some, I called it A, yeah, I don't know, A1, AM, some tuple of, so these are all in Mn of F and K, which will be this E1. Which will be in MD. So let me denote. I would put a tensor product here if Ankit wouldn't be in the audience, but let me put a circle here. So this will also be a tuple. It's a tuple that appears here when we evaluate the x's, when we plug a's for the x, right? So A1 tensor D1 AM tensor DM. And what turns out, this is a connection really to the non-commutative rank I described before, is that the non-commutative rank, which I don't define, but now it will be a definition for it, a non-commutative rank of L is n if and only if there exists a D, and it just follows from the definitions, if there exists a D and such another and such a K, such that the normal rank of A L K is n times D. So the only way you can be non-commutatively singular, a tuple of matrices, this L is, we should think of it as some AIXI. This is non-singular non-commutatively if it is non-singular commutatively in a blow-up of the space. Okay? That's what it is. For the commutative question, this D equals 1. Otherwise, it can be some big thing, and we want to show that it's not too big, that the D which achieves this, so it's either this or less than n in which there is no such D. Right? So we want to distinguish these two cases. And we want to ask what is D star, the smallest place where we can stop, so that after it, we know that if it was non-singular for all the blowups, for all the Ks up to this D star, then it will continue to be non-singular forever. Okay, so I want to prove this. So what exactly am I proving? Let me denote. Here. For any D, I want to denote rank D of L. Right, and this is interesting for every D. It's simply the maximum, so it's motivated by this. The maximum over all these choices of K, D by D, the maximum of the normal rank, rank of L K divided by D. Okay, so I blow up the space by D, so I normalize by it. Okay, so this is a number, this, or maybe I want, let me not normalize it. Okay, so this number is, I won't normalize it. So rank D of L is a number between 0 and D. Okay? So what we want to prove is that we want to prove is that if there is such a D, then this D has to be small. So I want to prove that if non-commutative rank defined this way, non-commutative rank of L is full, then there is a D which is less than, I'll prove n plus 1. Like that. So this basically D star is at most n plus 1, which is just a bit worse than I promised you. Okay? So how can you prove this? There's an amazing ingredient that comes into it that I'm not going to prove. It's a result of the same IQS in a different paper, which says that this maximum for every D, this maximum is always divisible by D. There's quantum jumps, whatever. So D divides, so this for every D. For every integer D divides rank for every D, for every L. So you start just with this tuple of n by n matrices, and then you blow them up. If you do it in the best possible way, you choose the DIs in the best possible ways as D by D matrices, you will always be a number that divides D. The proof of this is not so difficult if you know something else that's sort of amazing. Maybe I will skip writing the definition of it, but this follows from a result from the 1950s of Amitzur in the study of non-commutative fields. And so, these connections go all over the place at this very basic result. And using it, this is not difficult. To prove this, even this, I think today is not too difficult, right? I mean, we think we have a dream of writing up all these results in an intelligible way. They have simplified over the years, but you will not guess it if you look at the appropriate books and papers. So anyway, so this is a fundamental fact. And using this is like a two-line proof. Okay, so everybody is with me. Any questions?
So this is where somehow the specific problem comes in.
Yes, that's exactly, this is where. Actually, things of this nature occur all over invariant theory. Let me give you, I was going to do this example of discriminant and action on polynomials, which I will not be able to do. But remember I talked about taking a homogeneous polynomial. Well, let me just write it here. If you look at the action of SLN on polynomials of degree d in x1 through xn, and I, so what, p of x goes, if I have a matrix A here, goes with A to p of ax. Okay? It turns out that the invariant polynomials here, so this action has an invariant ring, and it has polynomials in it. All the polynomials in it, the degrees are homogeneous. You can always assume that the invariant polynomials are homogeneous, because if they are inhomogeneous, you can break them to homogeneous parts, and they stay they stay invariant. So, so all of them, if you look at the invariant ring here, fg is some set of polynomials, and you look at they are homogeneous, like I said before. So the degrees of all pi's are divisible by n. There is this rigidity or regularity or whatever you want to apparent in other places. So this is similar, but it's not the same phenomenon. Okay. And I was also going to show you this, but I will not have time for that. This becomes evident from the Cayley omega process I mentioned in the beginning. So let me just prove this 5 minutes, and then we'll be done. So what can we infer from this? This is a really useful fact. So first I need another trivial lemma about this rank D of L. So I claim that rank D of L is at most rank D minus 1 of, D minus 1 of L plus 2n. And this you should see with the naked eye. If you write, so suppose we take L composed with K, we blow up by D by D matrices of some, and we write it as D blocks of n by n. So each one of these is n. Right? I'm writing the tensor product in this fashion, and there are D parts of this, and similarly here. Then you can see that if I just look at this part, that's if I take, so this is 1 to up to D minus 1 and D. If I take just the D minus 1 by D minus 1 part, it's part of the blow-ups by matrices of rank D minus 1. So I can take the worst thing here, which achieves RD minus 1 of L, and then whatever else, whatever you take in filling up in K that are responsible for this part, you can increase the rank by at most 2n. And here, and then you're just adding n rows and n columns to the matrix, so you cannot increase it by more than n. So that's easy. And now, the punchline. So this is a simplification. This D plus 1, this n plus 1 upper bound, which I'm proving that is slightly worse than the n minus 1 of Derks and Markham, is also due to this IQS. And what they say is the following. So you observe this, and then you say, well, suppose that D star, suppose we know this star, so is something. And suppose actually it's, well, anyway, suppose we know this star. Then we know that with D star minus 1, the rank is not full, is not n times D minus 1. So again, what do we know? We know that the rank of D star minus 1 of L, we know that it's at most, it cannot be equal to D star minus 1 times n. Right? Otherwise, this star would be 1 smaller. Okay, so this we know. But by this rigidity, what can we infer? We can infer that rank this star minus 1 of L is actually much smaller than this, right? What should it be? No, it should be n minus 1. It should be a multiple of this. So this at most, this star minus 1, n minus 1. And here you win. That's the place you win. On the other hand, by this lemma, this is at least like this star. Sorry, this is yeah, like this star of L minus 2n, which is equal. Now we know that this star was chosen, so it's this star times n. So we get here this star minus 2n. So you compare these two objects, and you see that this star cannot be more than n plus 1. Yeah, I think I'm on time for this, so thanks.